So in this lesson, typically we talk about what are different standards of metals. So we know the properties and composition, but standards do give a headache to industry because you need to know how to compare the standards. And we also talk a little bit about how do you select the right material for the right application. So this is from designer's point of view. Foundries have no choice, but designers have a choice, and I want to make a case that choose the right material for the right application. And how to do that, a little clue about that will come. Now your various standards, starting from your Japanese to DIN standard from Germany, France, UK's BS standard is very famous, then your ISO standard. India has its own standard called IS, so IS should not be confused with ISO, right? And these are not exactly equivalent. I mean, if you look at the composition, you will find slight differences in those things. So there's still a need for a nice selection software, and maybe I'm talking to students now. A software where if you say, okay, as per JI's standard, this is the metal which the customer wants, but I go by this standard, and what changes should I make to my composition to get that standard? Or what are the difference in give and take? What do I lose in properties? So can we have some kind of a nice software for, and it's a good student project here. So, and then for ductile irons, similarly aluminum alloys, and then you have aluminum alloys, a large number of classifications are there. So this hopefully, if you don't have this comparison, maybe this will help you, but many other industries do have these comparison tables. Now let's come to properties. Okay, we usually talk about only mechanical properties. So we say strength and your hardness and ductility and elongation and maybe fatigue limit or impact strength and things like that. We do not talk about physical properties much. Okay, but the fact is that we have to know the values of these physical properties to be able to cast properly and to track what is happening in the foundry. So for example, density at liquidus, density at solidus, density at pouring temperature, density at ambient temperature, you need to know the values. Okay, otherwise you do not know what is happening to the casting and the mold. Similarly, thermal conductivity, specific heat, even your thermal expansion which controls your dimensions, these are important physical properties that we need to know. And these values are not available for detailed alloys. Maybe it is there for aluminum, pure aluminum or for steel, but not for various aluminum alloys. What is the difference in that? These data are not available easily. And again, we need to generate that as a national project perhaps. Chemical properties, we are not much worried, but these days as we worry about environmental concerns, the toxicity of metals, okay, does start becoming important. And when you use these castings for food processing or medical implants, it becomes really critical. So chemical properties of different compositions, again the data is not available easily. Okay. The last one is very important here, which is technological properties. Here we mean by technological properties, what is the machinability or castability or weldability or formability of the different metals. Okay. If I say castability, can I in one word can I define that? No. Has this been defined in any book? No. How do you measure castability? No one is talking about that. So we are trying the first attempt to define castability. Formability, to some extent it is defined. You have forming limit diagrams and other means of finding out whether how easily formable a particular material is, not casting. So we need to look at that. And finally, not to forget the cost of the material itself, which seems to be changing on a daily basis all the time significantly, and it created a lot of hassle last year and the year before that for the foundry industry. We need to track that. So can we have a web-based tracking of costing in some way? And for a particular composition, can we track the costing for that? So these things should become slowly available for us. We can track the temperature and humidity in different cities all over the world. So why can't we track for a particular composition what is the cost today that I should charge the customer? A web-based application for that. Okay, so these are all ideas students should note down and think about that. Now also, when you say properties don't come from composition alone. What we should not forget is they also come from the processing route and parameters that we use, and also finally the microstructure that we get. And this is the holy grail of metal casting today. Can we design a composition and the process parameters to get a particular microstructure and thereby the properties? This is the holy grail. Reverse engineer. Don't wait for the structure to come and then measure the properties, but predict and get the properties that you want by design, by process. This is what everyone is trying all over the world today. And this depends on many parameters in the foundry, including not only your pouring temperature and modifiers, but also cooling rate and strain rate and treatments after that. Ideally, you want to minimize the heat treatments because that's additional cost. Okay. Now, there are already good relationships between structure and properties. So if you know the structure, you can predict the properties, especially your hardness and strength. And relationships are existing to predict that. For example, here looking at the grain size, different grain size, and from that you have the root over D, and from D if you plot, you can get the yield strength. So it's possible to compute the yield strength of various metals once you know the grain size and composition. Now these properties are not constant. They vary by temperature to start with. So when you're looking at applications, you have to find out my working temperature conditions or my extreme conditions, what material I need to use. These are available, and you can see some interesting things like aluminum at one end, okay, for low temperature applications, to nickel superalloys at high temperature. Even better than that, if you want to go, is you have to go for ceramic applications. So metals have their own limitations. But turbine blades, for example, have a lot of nickel content and chromium content, which gives you high temperature strength. Now there's a famous professor called Professor Ashby at Cambridge University who created these interesting diagrams, and these are called as Ashby's diagrams. What he has done is he plotted various properties against x and y axis. So here you see the density along x axis and the strength along y axis. And if you see, interestingly, at the lowest, right, they seem to have density around 5000 and strength around 1000 MPa. Okay, but if you really want, and if you go to right side, if you see lead alloys, high density and low strength, so you don't want to use them for high strength applications. So this gives you a starting point of how do you select materials from strength to weight ratio. Now next is, if you see the from our foundry point of view, our pouring temperature and melt energy required. And very interestingly, if you see aluminum, the pouring temperature is not very high, but the melt energy required is very high. Very surprising result here. Okay. Whereas if you see copper, it's a higher pouring temperature, but the energy required to melt copper is not so high. One reason why you see again all the old castings is bronze castings is because it's easy to melt with a very low level of energy. Okay. Interesting. So this is an example of plotting of various kinds of graphs to help designers and manufacturers. Okay. So what we talked about was in this lesson, you have a variety of metals and alloys available. We have various standards for that, but standards themselves are changing. Standards are not necessarily latest. People come up with new compositions all the time to achieve a different set of properties required for a particular application. So don't always select from a basket of known materials. Just go and look for new materials all the time. Only thing you may have to look for the processing parameters to achieve the right properties. But if you do that, you start beginning on the road to core competence. Your core competence should be the combination of metal, process and applications. And if no one else can produce that combination and there is a sufficient requirement for that, you are king in that field. Okay.